Our next speaker is Zoltán Füredi, talking
Oh,
about
thanks.
Sidon Sets also.
Yeah, thank you. Thanks for the invitation. And I am really, really envy how much energy you have to organize such a meeting over 100 participants in these times. Uh, so uh, I use the pointer, yeah. Okay, so as you see, I am stuck here in Hungary in the last year. Um, Only we return later in the summer. But anyway, let's start with mathematics. I am going to talk about Sidon sets, and you all have this abstract that the main thing here is that a slight improvement on the upper bound on the maximum size of a Sidon set of the first integers. And on this slide, the most important thing are the names of my co-authors, Yoji Balog and Shoktik Roy. Uh, so this is the summary of the talk. Uh, everything I will talk about will be elementary, absolutely elementary. So I'm going to start with a commentator inequality, which is itself is very nice, but of course well known. And then using that inequality, I'm going to present a proof, or at least a sketch of the proof for the maximum size of a Sidon set. And then there is a one-page proof by Lindström. And then in the last part, the second part of the talk, we just combine the two, how to get a slight improvement. Okay, so that's the plan. And let's start with this inequality, which is about hypergraphs. And it really came from coding theory back in the 1960s. And basically it says that if you have a hypergraph, if you have a family of sets where the intersections are small, then the union is large. It's quite natural. So here is the precise form that if we have m sets, m will be always the number of sets. And we have at least k element sets. So we have m k element sets, small intersection, or small pairwise intersections. Then the union is at least something like, you see here, something k squared over t. So we always think that m is large. We have many sets and many k element sets. Then the union will be something like k squared over t. And this is a kind of the best possible bound. Even equality can hold for several values. There's a large area of mathematics when they investigate the equality case. For example, finite projective planes are such a class, and other nice symmetric structures. The proof of this is, well, it's only one page, that we have k element sets, well, at least k element, but of course we can say that they have exactly k elements. Intersections are small, and we just consider how one set intersects the others. So here I is fixed, AI is fixed, and we consider all the intersections all the intersection sizes and add them up. Now, if we intersect with itself, we got K. Otherwise, we have an upper bound T. So we have to add up this quantity here m times. And that's an upper bound. And well, as usual, we have what we did, well, we consider from the other direction, the same matrix, we consider the degrees, and of the hypergraph, and we got every degree exactly as many times as we counted, so we got the square here, consider the Cauchy-Schwarz, and got the bound. Okay, so that's the so-called Johnson bound. And actually, we consider the T equals 1 case, basically. So, okay, so the next topic is just how to apply it for Sidon sets. Well, I think here in this audience, everyone knows what a Sidon set is. I just read a few things to get used to my handwriting, sorry. So we have a k-element set of integers. Here n is the set of first n integers, and we call it Sidon set if pairwise unions, pairwise sums are distinct. And the question of the size of the larger Sidon set was proposed in, well, almost 100 years ago. It's very interesting that actually Sidon himself, also Erdős, were students of Feyer. And so they had to learn Fourier series. And Sidon got this Sidon set investigating some Fourier series problems. And as Paul Erdős mentioned in many of his talks, when Sidon told him that he was able to construct a large Sidon set of size at least n to the 1/4, then he immediately constructed, just using the greedy algorithms, he just constructed a Sidon set of size n to the 1/3. And we have a trivial upper bound, root n. All the pairs are distinct. So all the pairwise sums are distinct. So they were working on it a few years and got this nice result. Erdős and Turan published in 41 that actually the size of the larger Sidon set and among the first n integers, something like root n. And they only proved the upper bound because the lower bound, which is algebraic, and there are different versions by Bose and started with Singer. There is a root n times some particular one lower bound construction. Now, in 1969, Lindström gave a different proof, well, somewhat different proof. This was slightly improved by Sileruero by 1/2 in 2010. And okay, so let's overview these proofs. What are the ideas of these proofs? Actually, our proof will be basically the same what Ruzsa did, who claims that it's the same what Erdős and Turan did. And also Benny Green has a paper where he used the basic Fourier method and he also mentions that actually his proof is basically the same as Erdős Turan. And it's a long-standing unsolved problem. What is the true order of magnitude of the error term in the upper bound? I have found two places where Paul Erdős offered a serious prize to prove better upper bounds. Now, we were able to improve the root n, the force root n, by 0.2%. So, well, I think as a gentleman he was, he would probably send us 0.2% of the price, although, well, we are very far from the truth. And also, you will see the ideas does not seem to be applicable, but anyway, it's an improvement. Okay, so what were the original proofs? The root n, force root n plus 1. Take a Sidon set and consider all the shifted sets. Okay, so we make a hypergraph by shifting the Sidon set m times. And the main point is that these sets are almost disjoint. There is no intersection size 2 or larger. So we can use our inequality. And we got this n plus m minus 1 is at least I mean, that's the size of the underlying set. Okay, so we have an n element set. There's a Sidon set in it. And we shift it m times, where m will be, as you see here, n to the 3/4. Sorry. So the left-hand side is about n, slightly bigger, because we have m copies of the Sidon set. And the right-hand side is the inequality, the Johnson's inequality, k square m over m plus k. We can rewrite it like this. We got n is at least k square, subtract m minus 1 and subtract k cube over m. Obviously the best if we can choose m, we can choose any m we want. And if we choose m as k to the 3/2, which otherwise means m to the 3/4, then we got the bound. It's a regular calculation. So that's it. That's a nice elementary proof. Lindström proof is somewhat different. Here, instead of shifting the set, we consider the differences, and we say that a difference aj minus ai has order j minus I. So if you consider the order 1 differences, then they add up, and add these differences up, we got something which is less than n. And similarly, if we add up differences order r, we got something less than r times n, because we have r ways to start this telescope. So we consider L layers. So altogether we have L times L plus 1 over 2 sums. So this is L plus 1 choose 2 times n. That's an upper bound for the total sum. And on the other hand, these numbers are all distinct. That's where we now use the Sidon property that if in the first row we must have at least k-1 different distances, and in the second and the third row there should be at least k-2 and so on. So altogether we have at least k times L minus L choose 2 different numbers. So this sum here is at least the sum of the first k times L minus L plus 1 choose 2 numbers. We know what is this sum, and if we compare the upper and lower bounds, we got what we wanted to. Now, again, n and k are given, and we can choose L. And here is an important remark that we can choose L as we like, and then we got this red upper bound here. And that's an important kind of generalization. We will choose L in a slightly different way later. Still, we know that if we choose L in a slightly different way, this middle sum here is almost the same. Okay? So there is it's a paraboloid, or actually hyperboloid, doesn't matter, but it's very flat. So how to improve Lindström bound? Well, we have an upper bound and a lower bound. So if we know something about the difference, if we know, if you knew that the upper bound is much bigger, okay, so we just take this sum, well, or the sum up to order, or the difference is up to order L, and the sum of the first integers up to L times K. Now, we know that this is non-negative. That was the essence of the proof. But if here we have many, many long intervals, then we got an improvement. So we just take this difference, by C, and plug it in the previous formula, we got a better upper bound. So the larger the C, we get a better upper bound. And here comes that we can choose alpha as we like. So if this term here is sufficiently large, we got an improvement. Now, what about the other proof by Turan and Rura and others? We have a hypergraph. The same Sidon set A1 shifted m times, where m is something n to the 3/4. Now, it's very clear. Here's this one-line proof, what we already have seen. Now, what is the weak point of the proof? The weak point is that at the very beginning, in the first m integers, first m points, this hypergraph cannot be very dense. I mean, at element 1, the degree is only 1. The average degree is about 4 through 10. So at the beginning, the degrees are smaller. So this the Sidon set must have some kind of irregularities. There should be a large variance. Okay, so if you know that the variance of the degrees is reasonably big, then we got an improvement. That's the other observation. And the final step is that we have two different upper bounds, and somehow they don't fit together. So either C or K is large. So so now comes the most important step here, that we have the hypergraph, we have the shifted hypergraph obtained from one Sidon set on n elements, but now we have n plus m elements, n plus m minus 1. M is small, n to the 3/4. So this m is actually very small. But we separate the first 3% of it. And because we wanted a positive fraction, so this beta is 3%. So if in the first 3% the degrees are small, then we got a large variance. So in the first 3%, that's what we got. In the first 3%, we have to have quite a number of members of the Sidon set. Otherwise, we are done. And we can make the same with the last 3% of the first M. So basically what we observed, we prove that if we do not have, so if the Sidon set is large, as large as the Erdős-Turán bound or the Ritzren bound rather, then in the first 3% of the M elements, there should be many members. And after that, there should be a large gap. So what this means, that if there's a large gap, so here there should be only at most 6% of what is possible. So this gives us plenty of long intervals. So, and that's just a little calculation to complete the proof. Now, that's a calculation. Now, we can have, this way we can prove only some small gamma, positive gamma. When we wrote down, of course, we took both ends, we considered both ends of the interval, because the Sidon set is kind of symmetric, or the hypergraph is kind of symmetric. But anyway, the main point is, again, this figure here, that in the first 3%, there should be many elements of the Sidon set, many more, otherwise the variance is small. And then there should be a large gap, otherwise the variance is small. Now, and that's the whole thing. Now, how we can go further, it's not clear. We tried, obviously, if we have a chunk of the Sidon set which is relatively dense, and then another large part which is relatively thin, then there should be another dense part, and then should be another thin part. So there should be some kind of waves, but we were unable to handle that. Further. So after a while, it becomes quite like a random sequence. So that's all. Thanks for the possibility.
Zoltán, thank you very much. Are there any questions? So let me give time for people to actually type in the Q&A, and we'll see. So Kevin O'Brien has a question.
Yeah, I see. If well, we didn't check that. I'm sorry. Or we didn't calculate what end node we need. It's probably very small. So maybe there shouldn't be any end node here. So, but we were a bit careful with the calculations to be sure. So.
Any other questions for Zoltán? I mean, it took 50 years at least before anyone could improve this estimate on Sidon sets. So it really is a fantastic result. I mean, it's far from the truth, whatever the truth might be, but to even get your 0.2% is a wonderful thing.
Yeah, thanks for the kind words.
If there are no other questions, I thank all of the speakers so far today, and we have a 30-minute break. So Zoltán, if you can close your screen share.
Yeah, I do.
And we start again in 30 minutes.